Hi and welcome back to another lesson in the physics video series. Today we're going to do an inclined plane practice problem. Here we have a mass of 10 kilograms to be released on an inclined plane. We are going to calculate all of the components and the friction and do an analysis of this problem. Let's get started. The first thing we're asked to do is draw and compute the following vector components: the weight, the parallel, the perpendicular, and the normal. The weight is this black vector, which is equal to mass times gravity. The mass was given as 10 kilograms multiplied by 9.8 meters per second squared gives us 98 newtons. Out of those 98 newtons, they are distributed amongst the parallel component and the perpendicular component respectively. The parallel component, which is the green vector, is equal to F sine theta. As we learned in the last lesson, the parallel component is opposite of the angle, and that opposite goes with sine. So it's the weight from step 1, 98 newtons, times the sine of the angle of 28 degrees, which is given in this problem. The perpendicular component will be the weight times the cosine of 28 degrees. So here we have 46 newtons parallel force and 86.5 newtons, which is the perpendicular component. The green vector parallel component is the accelerating force. That's the force that pulls the box down the ramp. Now at the moment, it doesn't seem like there's a use for the perpendicular component, but we calculate the normal line, which is equal and opposite to the perpendicular component. And this is the vector that holds the box up or keeps it from falling through the surface of the ramp. So a portion of the weight, the blue vector's perpendicular component, really would like to pull this box through the ramp, but the ramp resists it and pushes against it with a force equal and opposite to it, which is the orange normal force. So whatever the value for F perpendicular is, that is the value of the magnitude of the normal force, except it is in the opposite direction. Now let's calculate the acceleration down the ramp. We know that F equals ma, and F parallel is the force that pulls the box down the ramp. So if F parallel equals ma, A is equal to F parallel divided by m. Canceling m's, we get g sine theta. The sine of the angle is sine of 28 degrees, which makes this a portion of the full gravitational acceleration of 9.8 meters per second squared. So this box accelerates down the ramp at 4.6 meters per second squared. Let's now calculate the coefficient of static friction. If the box does not move down the ramp, then the force of static friction is equal to mu times the normal. Solving for the Greek letter m, mu equals friction divided by the normal. We know that in the case of an object that it's not moving, the force of friction is equal to the parallel force, and we know that the normal force is always equal to the perpendicular component. Setting these two into their full trigonometric forms gives us mg sine theta over mg cosine theta, canceling the mg terms, leaving us with tan theta. To find the coefficient of static friction, we simply take the tangent of the angle of the incline, and tangent of 28 degrees gives us 0.53. Now, if this was a problem off of the Regents, we could then go to the Regents reference table and find what 0.53 is and tell you what the surface is made from. And finally, what is the force of kinetic friction if the object slides at a constant speed? So this concept is very simple, that the kinetic friction force is equal and opposite to the parallel component of the weight when there is no acceleration. So the force of kinetic friction is equal to the F parallel green vector, and that was calculated in step 2 as 46 newtons. The accelerating force pulling it down the ramp is balanced by the force of friction dragging up the ramp if there is no acceleration down the ramp. And there you have it. This is the 7 steps of an inclined plane practice problem. I hope you enjoyed this video, and thank you for watching. We'll see you in the next video.